Next, we go to theorem number 6. This is known as left axiom group. That means in a semi group, if left axioms are true, then automatically right axioms follow. Again, if left axioms are true in a semi group, then automatically right axioms follow. Then semi group becomes a group. We go to the formal statement. G is a non-empty set equipped with a binary operation. Then G dot is a group if condition 1 bracket A dot B dot C is equal to A dot bracket B dot C for all A, B, C belong to G. Condition 2, there exists E belong to G such that E dot A is equal to A. Condition 3, there exists A inverse belong to G such that A inverse dot A is equal to A for all A belong to G. Then we have to show that G dot is a group. Conditions are given here if condition 1, condition 2, condition 3. What is condition 1? Condition 1 means it is a semi group. Condition 2, E is a left identity element. Here E works as left identity element. And here A inverse works as left inverse. We have to show that automatically E becomes right identity and A inverse becomes right inverse. Here it is given a semi group. G is a, if the condition 1 says that is a semi group and left identity exists, right left inverse exists, and we have to show that E works as right identity and A inverse works as right inverse. So we go to the proof of the theorem. To prove this left identity is equal to right identity and left inverse is equal to right inverse, we need one more condition, that is left cancellation law. So first we derive left cancellation law hold good in the group, in the semi group G. First we prove left cancellation law hold good in G. Note that E is left identity in G. Let A, B, C belong to G. We are considering three arbitrary elements in the semi group G. If A belongs to G, then as in the statement left inverse exists. A inverse is the left inverse of A in G. Thus A belongs to G implies A inverse belongs to G, and A inverse is left inverse of A in G. Now consider the equation like this: AB is equal to AC. We have to prove that left cancellation law hold good. So I am taking AB is equal to AC. Operating A inverse on both sides for this equation, A inverse bracket AB is equal to A inverse bracket AC. Using associate laws and changing brackets for this A inverse A, read as bracket A inverse AB is equal to bracket A inverse AC. And this becomes EB and this becomes EC. EB is equal to EC since E is left identity. Don't say identity element. In the statement it is given E is the left identity. So since E is left identity, here we can get B is equal to C. Here we have taken AB is equal to C and we have arrived B is equal to C. That means left side A is cancelled. So left cancellation law hold good in the semi group G. Okay. Next, we show that E is the right identity element in the G. A belongs to G implies A inverse belongs to G such that A inverse A is equal to E. As in the statement, A inverse left inverse exists. So I am using that condition. A inverse is left inverse of A. And we have to show that E is the right identity. So for that, consider A inverse AE. Consider A inverse bracket AE. Use associated law here. Changing bracket for A inverse A, we get A inverse AE and this becomes E from this part. So here it is EE. E is equal to E. And again I will write E as A inverse A from this. E is equal to A inverse A. E is equal to A inverse A. Thus we have, here it is A inverse AE and here it is A inverse A. Here it is A inverse AE and here it is A inverse A. So here see this one. For this equation on left side we can see A inverse and A inverse. So as we have proved in the above, left cancellation law hold good in G. So we can cancel A inverse on the left side part. So we get AE is equal to A. That means E is right identity. Here we have taken any element A. A is not a particular element. Let A belongs to J means A is any element. So for any element A, we have proved AE is equal to, that means E is right identity. The statement it is given E is left identity. Here we have proved that E is right identity. So we say that E is identity element in G. Therefore, E is also right identity of G. Therefore, AE is equal to EA is equal to A for all A belongs to G. So, identity element exists in the semi-group G. Now we show that A inverse is right inverse of A in G. In the statement it is given there exists left inverse. So we are taking left inverse and here we prove that same A inverse works as right inverse of A. Again I will write A belongs to G plus A inverse belongs to G such that left inverse A is equal to E, and we have to show that A inverse works as right inverse. For that consider A inverse bracket AA inverse and use the associate law, change the bracket A inverse A inverse. Here it becomes E and this is A inverse, EA inverse. Since E is identity element, we get A inverse. I can say E is identity element. Already have proved E is right identity. So I can use the word E is identity element. Of course, here it is left identity, no problem. So it is EA inverse is equal to A inverse. And again, since E is identity element, this can be written as A inverse E. E is both left identity and right inverse, right identity. E is both left identity and right identity. So I can write A inverse is equal to A inverse. Now, these two are equal. Here it is A inverse, A inverse. Here it is A inverse E. Here it is A inverse, A inverse, and it is A inverse E. See this here, for this equation on left side, here it is A inverse, here it is A inverse. In the first part, we have proved that left cancellation law hold good, so we can cancel A inverse here. So we get A inverse is equal to E. That means A inverse is right inverse of A. A inverse is right inverse of A. Therefore, I will write A inverse is also right inverse of A in G. Therefore, A inverse is equal to A inverse A is equal to E. Thus, all the axioms of the group are verified and proved. In the statement, it is given that G is a semi-group. G is a semi-group. Associate law holds good. And left identity, left inverse. We have proved that thus left identity is same as right identity. Left inverse is same as right inverse. So, 4 postulates of the group are verified and proved. Therefore, we say that G is a group. Here, I will write a formal way. Here, therefore, every element in G possesses inverse element in G. Thus, all the conditions of group are satisfied and hence G is a group. Likewise, similarly, we can define right axiom group. If left axiom theorem is there, so we can define a right axiom group also, changing the conditions in a right way, right side part. I will give the statement here. Right axiom group. G is a non-empty set equipped with a binary operation. Then G dot is a group. If condition 1 semi-group, that means bracket A dot B dot C is equal to A dot bracket B dot C for all A, B, C belong to G. Condition 2, there exists E belongs to G such that A dot E is equal to A. That means E is right identity. And condition 3, there exists A inverse belongs to G such that A dot A inverse is equal to E for all A belongs to G. That means A inverse is right inverse of A. Here it is a semi-group. Right identity exists and right inverse exists. Likewise, in the above, we can prove this theorem also. I leave this to the student. It is very easy. In the theorem number 6, I have explained left axioms. So, likewise, student can change the steps for the right axioms. That I leave this to the student as an exercise.